Hello, today we're gonna just solve a random LeetCode problem. So before I proceed to read the problem and try to solve it, I'm gonna let you pause the video here if you want to solve it yourself, which I completely recommend. And in a few seconds, I will show you a list of timestamps which you can use to navigate through the video and look at my different approaches. And the very final timestamp will be the solution of this problem explained in hopefully a very nice manner. Here's a list of timestamps if you want to skip ahead. I recommend listening through the whole thing if you want to learn how to answer maybe an interview question or how to think, but the solution should be at the very last timestamp. Let me start with reading what the problem is. So, container with most water. You're given an integer array height of length n. Oh, that's interesting because you're just given one argument. Okay, I guess n is just a random variable, which is the size of this vector. Okay, there are n vertical lines drawn such that the two endpoints of the ith line are I0 and I height 1. Okay, so that means if this is my line, this is I0 and I height 1, so we get the height from the array. Find two lines that together with the x-axis form a container such that the container contains the most water. Okay, return the maximum amount of water a container can store. Notice that you cannot slant the container. So let's look at the example. It's looking for the amount of water the container holds. So if I have this, the amount of water I think should be 1 times 1. And they've highlighted this as like the solution. So the thing in red is the solution. And this has 7 over here, so 1, 2, 3, 4, 5, 6, 7, yeah. And the height of this, so we look at the smallest bar, and that has a height of 7, so 7 times 7 is 49, and that's actually the output of this. So I understand what they're trying to ask us for, because like the amount of water in this container will obviously be larger than the amount of water in this container. Okay. That's interesting. So let's first think about any assumptions that we're going to try making here. One, we're assuming the heights are integers, not decimals. That's important. The other thing is, are we assuming that there are lines, like these bars? So can the array have a length of 0? I guess the problem doesn't say anything about it. Wait, oh here, constraints. Okay. Okay, there's another example, but like this is fine. This just verified. This was the thing we talked about initially technically, but this being one though. Okay, the constraints are n is equal to height.length, or dot size for a vector, I guess. And okay, n is at least 2. So that's a constraint that they mentioned, so we don't have an assumption anymore. We know that n is between this and that, and a height cannot be negative. So that was another assumption I was going to ask. So height can be a minimum of 0 and a maximum of 10 to the power of 4. Are there any other assumptions I'm going to be making? None that I can foresee at the moment. I'm just assuming that the width is 1 based on the examples, like the width between these two bars. But yeah, that's the problem. So let's start off with a brute force solution. I'm going to make a note here just because it's easier to like compare solutions at the end. So the first one I'm thinking of is like a brute force solution where we start off here. We look at the amount of water contained by this container, and it'll be 1 times 1. Then we look at the amount of volume contained here. It'll be 1, which is a minimum bar length. And then the width here, which is 2, so 2. And we just store the max of this and like the previous value. So that'll be 2 as the amount of water. Then we look at this. This will be 3. as the amount of water, and that's so we store that because that's our maximum value. And we do the same for this one, that one, that one, and that one. So all the containers starting at this point. So that would give me a maximum of 1, 2, 3, 4, 5, 6, 7, 8. So a maximum volume, sorry, maximum amount of water as 8. And then the amount, so then we move on and we start from here instead of this, and we repeat the same approach, right? We just continue. We have the maximum from the previous round and we compare that to the amount of water here. So the amount of water here is 6 times 1, so that's not bigger. So 8 is still our maximum. Then we come here, the amount of water is 2 times 2, 4, that's not the maximum. And we do the same until we reach the end. And in this case, well, based on the output, we know this is 49 because it's 7 times 7. And then we do it for this bar and then continue, and this bar and continue, and so on and so forth. So the same process repeated for each of these bars. And in terms of runtime, we know that doing this is O of 1, so calculating the amount of water is O of 1, but we're doing this n times because we have this starting point, right? If n is the number of bars, as assumed over here. So this would be O of n, but we're going to repeat the same process for every single bar. So it'll be approximately O of n squared for the runtime. Okay, so runtime is O of n squared. And what about space? In terms of space, this would be O of 1, because the only thing I'm really storing is the maximum value, and that's going to just be that maximum value irrespective of how many bars we have, right? If we have 20 bars, we're still storing one maximum value. If we have 200 bars, we're still storing that one max value. So this is my brute force approach in terms of runtime and space. But what else can I do? Okay, let's think. I feel like you can use dynamic programming here, and I've not used dynamic programming in the longest time. I know about it, and the way dynamic programming works is you just use the solution that you calculated in the previous phase or in previous phases to come up with the current solution. I can do a video about it later, but that's what dynamic programming is at the core of it. And it's not really used, I mean, I've not seen it being used as often in industry, but it's still a concept that I think is useful to know because it can be helpful in certain problems. But let's look at this. If I were to use dynamic programming, the way I would do it is I would start off with like the amount of water contained here. Then to calculate the best amount of water contained like until this endpoint, I would use the max of this and of this. Okay. Then I come here. I have the result of like the maximum of this and this stored. Then I come here and then I calculate the max of this and the max of the stored result that I had from calculating the max of this and the max of this. So using that approach, I would do the same thing here. So I calculate the amount of volume here and I take the max of that and the max that I calculated in the previous step. And I can do that for all of these bars. Then I have to change my starting point to this and repeat the process. So I come here, calculate the amount of water stored, and then come here, calculate the amount of water stored. So it'll be the max of the water stored here and the water stored here. So in this case, I guess it's this. Then we come here, calculate the max of the water stored here and the water which we, so and the value we stored previously, which was like the max of this and the max of that. So we just take the max of that and then we repeat the process. I hope that kind of made sense. But that would be a dynamic programming approach. Does that help us? Let's see. It probably will. I don't know. Dynamic programming usually if used in the right context, it's helpful. But let me double check. I'm not too sure if this is what we should go for. So if I use dynamic programming here, what's going to happen? So in terms of runtime, for this one bar, I'm still going to be doing O of n work because I calculate the volume here, then take max for like these two, and then the max of those two, right? And then I'm going to do it for every single bar, so it'll still be O of n squared. Oh, this is not looking good because I am pretty sure this is not constant space. So brute force might be better. But in terms of amount of space, we would need to store the previous value here. So it's basically previous value and current value that's going to be stored. Because that's the only thing we need, right? We need to know the previous value and the current value. So that's going to be, yeah, we just need the previous value and current value. So irrespective of the number of bars, this is also be O of 1. So the previous maximum and the current value, and take the max of that and store that as the previous maximum. Yeah, so this will be O of 1 as well. So this is actually the same runtime and space complexity as brute force. And if I were to choose between this one and this one, I would actually implement the brute force one because it'll be easier to understand from the perspective of like whoever reads my code later on, because they're not as familiar with dynamic programming. I guess it might be fine, but I mean, there's not too much of a difference between these two. It just depends on who's reading my code, and I guess they both are fine, but I'm guessing these are not the best approaches. So what can I do instead? I can... Okay, let's think about this, right? I want the amount of water in the container. If I start from here, I can get it. It's the same thing if I start from the back, like this. Okay, so... Okay, let's think about this, right? So we want the amount of water in the container. We want the maximum amount that can be stored. So given that I'm starting here, we want to maximize two things. We want to maximize height and we want to maximize width. Because the more width we have, the more amount of water we'll be storing, given that height is constant. But we know that the amount of water we're storing is actually, in terms of height, going to be limited by the minimum of this and any other bar it sees. So we want to minimize... Okay, so we know this is a constraint. We know that the height is constrained by this. So the height is constrained by the minimum of this and whatever bar we see. But maximizing width is actually easier because you know you want to start off by like the maximum width, right? So we can start here and then we know this is fine, but since this is a smaller height, so smaller height, or even if it's larger height, right? No, okay, let's take the guess where it's a smaller height. Where it's a smaller height, the width is going to be less. And since this height and this height are both bigger than this, it doesn't really matter because it's all constrained by this one thing. So we don't even need to check the amount of water contained here. We can just stop here and we know that at this starting point, the maximum amount of water that we can have is just this. Then we move to the next starting point and we start here. So start at the end. And the amount of water in terms of height is constrained here. So if we're decreasing width, we only care about moving forward if this height is actually larger than this. Otherwise, it's useless moving forward, right? Because your width is going to decrease and your height is smaller as well. So we keep it here. Oh, I see. Okay, and then if we start here, the same process follows, right? The height is smaller, so we don't move on. Again, height is smaller, we don't move on. Height is smaller, we don't move on, etc. Okay, so worst case scenario, what can happen? The worst case scenario, okay, let's write this out. I don't know what you call this approach. I don't know what I call it, but I'm gonna say, okay, I don't know what to call this. Okay, last. So end to beginning approach. I'm making up this term. You can, I don't know, call it anything else. Because you're starting at the end, then moving towards the beginning. So end to beginning approach. So the runtime and space complexity, we'll talk about this soon. But I want to make sure I flesh out the logic behind this. So we're starting at the end, right? So we have a left pointer, which will start at the left or the start. And we're going to have a right pointer, which will start at the end. Okay. And then we move right pointer back one. So back a bar if and only if the height of let's think about this really quick. If this was smaller than this and this was bigger, yeah, if it's smaller, okay, if it's taller than this, we're losing one. Always constrained by that. Smaller. Right. Okay, so we move the right pointer back a bar if and only if the height of the next bar from the right is larger, so strictly larger. Otherwise, it doesn't matter, right? Okay. So that's nice. If it's smaller, if smaller or equal to, so I can just do this. If smaller than equal to, then we should break and move on to, break and increment the left bar, the left pointer, to move to the next bar from the left. And then we repeat the process, right? And this whole time, what do they want us to return? So the output here is just the volume, right? So we're going to be storing, so store max volume. Oh, okay, it's not volume, it's like units. Okay, max units of water stored by the container. Seen so far. So this is like just one variable for storage. And okay, if it's less than, we break an increment. If it's greater than, we just repeat this process, right? We repeat the process of, okay, if not, so if it's greater than, we just move right pointer and repeat the process. Oh, sorry, I opened up my, I'm not sure how to remove this. Okay, it's gone. Okay, yeah, so if it's greater than, we move the right pointer and repeat this process until, of course, you need to make sure we stop when the right pointer, stop when right pointer is less than or equal to the left pointer. So that can easily be a while loop, right? Yeah, this is a good approach. But let's think about the space and runtime. So in terms of space, I'm just storing pointers, and that's not going to be dependent on the number of bars. And I'm going to store the max unit as a variable, not going to be dependent on the number of bars. So in terms of space, we have O of 1, which is brilliant, because I'm pretty sure the runtime is less than O of n squared. Well, okay, in terms of runtime, the best case is when we have something like this. You have a taller bar at the end and a smaller bar right before it, because you'll always stop, right? So, am I missing something over here? Like, if this is taller, this one is also taller. Wait, could this potentially be better than this? If this was extremely tall, it'll be constrained by that. But even if this was extremely tall, and this was extremely tall, and you have this, or this greedy approach, could it potentially not work? Because if you move, let's say your optimal was this, so it's like extremely tall and extremely tall. Then if you start here, you won't move forward because this is smaller than you, right? Even though like this is infinitely tall and this is infinitely tall, so the obvious solution is like these two. That's not good. Okay, that's fine. Okay. So this is an issue. If the left bar is taller than the right bar, keep storing max. Wait, hang on. So this issue comes up when the left bar is taller than the right bar, but what if we move... Okay, instead of moving the left bar, we move the shortest bar. So move only the shortest bar. Because if you think about it, yeah, that would not give us the value of the amount of water in the container starting here, but eventually we'll still get the largest amount of water that can be stored in the container if we always move the smallest bar. So if we have a left pointer here and a right pointer here, if we move this one, because that's the smaller one, see, it wouldn't make sense if we were to move the bigger one versus the smaller one, because the bigger one would always give us some benefit as to like moving this. Moving this decreases the height. Sorry, moving this decreases the width. But then we want to still keep our height as large as possible. So we keep the taller one and just move the smaller one. Okay, so this will move and we have this and this. Then we move the smaller one. That's not great. Move the smaller one. We come here. Are these equal height? Okay, then we move one arbitrarily. So we stored this max, right? Yeah. Then we move this. Then we come here, here, here. And this would be our max, and we've seen it. And I believe this would work in any case. Okay, end to beginning approach has just improved. So this is end to beginning approach 1. So this had an issue. Okay, because it had a logical issue. So let's move to the next approach, which is end. Okay, always move shorter bar approach. And the way this works is, while we know that our left pointer is strictly less than, right? Because if they're equal to, then it's not great. So if it's strictly less than the right pointer, what we can do is say, okay, I'm not writing proper code. This is like pseudocode just for understanding. But while the right pointer is greater than the left pointer, what we're going to do is to store, let's make a variable, max water amount. So max water will just be max of the previous max water, right? Which I will initialize somewhere, and the value of the water in this container. And we'll worry about how this is calculated later. So the volume in this container is the volume between the right pointer and left pointer. So let's say water between left and right pointer. Okay, so we know that. We know max water, and this is going to be initialized to 0. Well, yeah, or I mean the minimum amount of water is 0. I would have initialized this to negative infinity, but the minimum amount is 0 anyway, so let's go with 0. And we know max water is calculated here. Now we need to move the pointers. So move either the left or right pointer, and we just get the min pointer. So if we know that the left pointer height, okay, so left pointer is going to be an integer. We initialize to 0 and then max height. But if the value at left pointer, so the height there, and the height is going to be height. So if this height is less than the height of the right pointer, we just want to make sure we move the shorter pointer. So I can actually make this a ternary. If we know that the left pointer is less than the right pointer, we want to make sure we move the left pointer, so it'll be left pointer plus plus. And otherwise, we want to move the right pointer. So the pointer will be moved. Oh, I forgot a plus plus. Yeah, the pointer will be moved, and then we'll come back here. Well, actually the right pointer should be decremented, right? Because we're moving down. And we keep repeating this, and we'll have our max water by the end of it. And in terms of, okay, let's say in terms of runtime, this is going to be O of n, worst case. Well, okay, O of n, because you go through all bars, right? Eventually. And in terms of space, so the space complexity, we're not storing anything other than like the height array. But assuming we're not counting for like the array of heights, then the space complexity will be O of 1. Because you just have the pointers and the maximum, which is going to be the same number of variables irrespective of the number of bars. So this is the solution I would go with. It's the best. So let's actually implement this. I think we spent quite a bit of while talking it out, but it's important to like come up with the best approach, figure it out, and finalize that approach, and then move on. So let's move on and implement this. Okay, no, actually we've technically already implemented it here. Well, let me change the syntax of this slightly to match C++. Okay, so let's move on to solving this problem, or explaining how it was solved. So the optimal approach here was to have a left and right pointer. So the left pointer will point to the leftmost or the starting bar, and the rightmost pointer will point to the rightmost or end bar. Now we're trying to maximize the amount of water stored in the container. If we were to move any of these pointers inwards, so if we moved this right pointer towards the left or the left pointer towards the right, we will always be reducing width. And if we're reducing or minimizing the width, we need to compensate for the loss in width in some other way. And the only other dimension we have here is the height. So we compensate for the loss of width by trying to increase the height of the container. Otherwise, we won't be benefiting in any way. So because of this, it makes no sense to keep our pointer on the bar which has the lower height. So because of that, we look at the pointer which points to the bar with lower height, and then we just move that pointer to the next bar. Again, we repeat the process. So in this case, we move this pointer, and of course we keep track of the max at each step. So over here, we had this volume, which worked out to 1 times 1, 2, 3, 4, 5, 6, 7, 8. So this was 8 units of water stored in that container. Then we come here because we moved our pointer. And in this container, we have 49 units of water because it's 7 by 7. Next, we move the shorter bar. But let's assume that the penultimate bar, so this bar over here, was somewhere around there. In this case, it would again make sense to move our right pointer here. And once we do that, we're gaining in height because initially the amount of water that was in our container was constrained by this bar, but now it's no longer constrained by that because it's not longer the shorter bar, but it's constrained by this one. And if this bar, which I'm now going to outline in, let's do, which color? Let's do dark blue. So if this bar over here was shorter instead, we would decrease the amount of water we could store in the container, but that's fine because we already stored the value occupied by the water in this other container before, and we're just going to take the max at the next step. So we take the max of that, which is 49, because 49 was the max of 49 and 8, and we compare it to the volume of water, the amount of water in this part. So this is 1, 2, 3, 4, 5, 6 times 3, which is 18. And the max of that is 49, so we keep 49 as our max value. We then reduce the size of our container again by moving the shorter bar. So we come here, and this becomes our new amount of water. And the amount of water here will just be 5 times 8, and that works out to 40, which is still smaller than 49, so we don't keep it. And again, we move the smaller bar. In this case, we can move either bar because they're the same height. So let's pretend we moved this one, and we have this amount of water over here. And of course, this is going to change on the next step. We would have the smaller bar move again, and so forth, until we just get a bunch of numbers and we're just taking the max at every stage. So 49 will be our final answer. And this approach works. So feel free to test it out on different examples. In terms of the working code, let me walk through my solution. Okay, so this is the code I wrote out I didn't explain it too much in detail earlier, but let me walk through what I've done. And the reason I didn't explain it too much in detail is because it's in C++ and not everybody will understand it completely or well. And the most important thing is the logic, but here's how I worked out my problem. So if I were to scroll up over here, there was the solution class, and then there was this function which started. So there was some function name, and then we started off with this line. So int max water equals 0. So we initialize this variable called max water, which is the maximum amount of water that we've seen so far. We then have the next line to initialize the right pointer, and that will just be at the last bar. And since we're starting count from 0, this will just be the size of the height vector minus 1. So we've taken care of that. Next we have int left pointer is equal to 0, so we initialize the left pointer, while our right pointer is greater than our left pointer. And the reason we have that is because if the right pointer equals the left pointer, we want to stop. Or if the right pointer is less than the left pointer, it means they've crossed each other, and it makes no sense to continue because you've already seen that container length. Or that length is definitely smaller than the maximum amount of water that you can store. So we have this loop, which is our stopping condition, and while that condition holds true, we're going to calculate the maximum amount of water, and that maximum amount of water will just be the max of the previous max amount of water and of the amount of water in the container at this bar. So we have this function called water amount, which takes in a left pointer, a right pointer, and height. And what that function does is it just returns the width, which is the right pointer minus left pointer, times the minimum bar height. So we are using a vector over here. In C++, you can use the .at notation to make sure your vector is not being accessed or out of bounds. Because if you were to use the operator notation, so if you were to use height operator, so that the bracket operator, left like this, so this will work as well. But the issue with this is there is no bounds checking. So if left was -5, for example, this would not potentially error. So there's a possibility that it might not error. But if I use the .at function provided by the vector library in C++, this would tell me that this definitely is an error, and that way my code is more foolproof and safer. Of course, in this example, we're never going to have left initialized to -5, but I think this is just a safer thing to do. So we just take the minimum of the two heights, which is basically what's happening over here. And yeah, that's how we calculate the amount of water in the container. So it's just height times the width. So that takes care of our water amount function. Going back to the while loop, we have height at left pointer. So we have a ternary over here. A ternary statement is just basically an if statement. And if this condition, so if the left pointer, the height there, is less than the height at the right pointer, we will definitely return, or will not return, but we'll just increment the left pointer. So we move the left pointer inwards, which is what the left pointer plus plus statement is doing. And with the right pointer, we want to move that inwards as well, so we decrement it. So we have minus minus. Okay, so that is our while loop. And at the end of that, we just return the max water, because that's the maximum amount of water we've seen so far. So that's our problem. Hopefully it wasn't too hard, but if it was hard, don't worry, you'll get better with practice, and hopefully this helps. yeah, so that's it for this video. Hope this was helpful, and thanks for watching.